Okay, this is question number 22 from the 11.3 homework, and I just free-handed it instead of going in and cutting and pasting, but it's a hexagon, so it's a regular hexagon, and that means it has 6 sides. And then the only thing they give you is that one of the side lengths is 7, and that's it. And if it's regular, that means all the side lengths are 7. So the easy one with all of these is once you have one side length, you have the perimeter. So in this case, the perimeter would be 7 plus 7 6 times, or you could do 6 times 7, and your perimeter would be 42. And again, that's the simple thing to find anytime you have a regular polygon. You're just adding up the same number, however many sides that you have. For an area of this thing, which is what we're after on this problem, we're asked to find the area. We have to use this formula that got introduced in this section, which is half times A, the apothem, times the perimeter. And the perimeter in this case is 42, so we can fill that in. And then in order to use this formula, what we have to do is come up with the apothem. And it's a tricky concept, so I'll just draw it in. You're looking to go from the center of the regular polygon to the side. And what makes that thing a center is every regular polygon, no matter how many sides it has, is inscribed in a circle. In other words, if we took each corner of this thing and drew a circle around it, that circle would touch all the corners. And I'm not going to do it justice here. That's pretty good, actually. That's what it means to be regular, is it means it fits inside a circle. And so what we can do then is say, okay, well, you know, we have this apothem, which is this distance from the center to the outside, and in the previous sections or previous problems it was given, or we could easily find it. On this one it's a little more challenging because there's nothing more in here to help us. So what I'm going to do, I'm going to switch colors one more time here just to indicate I'm looking for something else. I'm going to draw a triangle right there. Those blue lines are the radius of the circle. And if I draw a line to every single corner, they're all radius of the circles. So every single one of those. And thinking about what I just did to the triangle, if you think about those blue lines, I've got 1, 2, 3, 4, 5, 6 triangles that I drew in. I have 6 triangles that I drew in. So what I did was I split 360 degrees 6 ways, meaning each of those central angles is 60 degrees. If each of these central angles is 60 degrees, I'm just going to blow up that triangle I've got right here. That's 60. Here's that 7 that's sitting out there. If I know that's a 60-degree angle, and I know these are both radius amounts, in other words, they're both equal. If I have an isosceles triangle with one angle defined, I know these base angles have to be equal. Well, there's 120 degrees left over in the triangle to split up, meaning these are each 60 degrees. So all 3 angles are 60 degrees, meaning this is an equilateral triangle, so these radius amounts are 7. Okay, so to do this one, you got to jump through a few extra hoops, and this actually was covered in the section as a separate idea of splitting up a central angle, and now they're pushing the 2 ideas together on this problem. So both the area equation, as well as needing to go and find what that central angle was, and then use it to actually do more with the problem. So in this case, and I'll switch back to red, and I'm going to draw that apothem in here. There's that apothem. That's a height. So that's a height on a right triangle, and if we split that 7 into 3.5 and 3.5, I'm looking for the height, or you know what, let's just keep calling it A. That's the apothem. So that's that same red A that I drew up top. What that means is I can say A squared plus 3.5 squared equals 7 squared. There's other ways I could do this. I could use 30, 60, 90 shortcut, but I'm just going to solve it the long way and be okay with it. So I'm going to subtract the 3.5 squared from both sides. I'm going to square root both sides. And the reason I'm doing this without actually jumping over the calculator yet is now I'm just going to jump in the calculator and punch this in one time. So I'm going to do square root 7 squared minus 3.5 squared. And that's going to give me my apothem length. So square root let's see, where's my square root? There it is, 7 squared, which I know is 49, but I'm just going to write it as 7 squared minus 3.5 squared, and I'll close out my parenthesis and hit enter. Then 6.062, or let's call it 6.06, would be the apothem length. And now that I've got that, it is going to go back into this equation for area. So I'm going to do half times this times 42. Or what I could do is just go, I've already got that in the calculator. So times by 0.5, there's my half, and then times by 42. So I need those three things multiplied together. So there's the apothem times a half times 42. And my answer is going to be 127.31 if I round to the nearest hundredth, which is what we're doing in this section. Oop, I already forgot it. 127.31. So my area is 127.31. And that's it. So it's relatively challenging. So definitely a tricky idea to do on this one, but it is pretty similar to the other ones, with the exception of you do have to use this idea of splitting up the central angle to figure out that you've got this equilateral triangle. Without that, you won't be able to move the problem forward, but once you have that, then you can go and do it like you did the other problems.